Hey there, astronomy students. This is Miss Ruark. This is Vodcast 8.1 for Chapter 8. It's talking about the sun. All right, so the sun. That was cute. The sun. Let's talk about it. It's just an average star, which means that it's not too hot, it's not too cold, it's not too big, it's not too little. It's average. It's a G2 sun, or G2 star, which means that it's in the G classification. Remember, we've talked about the classifications of the sun or stars, and it's a subclass 2. Appears bright because we're so close to it. Otherwise, it wouldn't be that bright. Okay, how do we know? Absolute visual magnification is 4.83. Remember, the bigger the number, the less bright it is. The smaller the number or negative number, the brighter it is. So this is it's not that bright. All right, it is 109 times the size of the Earth and is 333,000 times the mass of the Earth. Now, you think, wow, that's really huge. Actually, it's really big in size, but it's really not that heavy in comparison to its size. It's mostly gas. Actually, it's all gas. Let me take that back. It's all gas, and its density is roughly about 1.4 grams per milliliter. The density of water is 1.0 grams per milliliter, so it's just a little bit more dense than water. The core temperature of it is about 15 million Kelvin, and the surface temperature is roughly at about 5,800 Kelvin. All right, so very important. Anytime you're looking at the sun, don't look directly at it. It can hurt your eyes. If you're looking at it through a telescope or binoculars, don't look directly at it. You got more focal power from the lenses. It can focus on your eyes and it can cause permanent damage. So don't do that. If you decide to look at the sun for any reason through telescope, binoculars, etc., use a projection technique or a special viewing filter. Otherwise, we really don't want you to lose your sight. Okay, moving on. The atmosphere of the sun. You have the photosphere, the chromosphere, and the corona. Okay, so these are only visible during the chromosphere and the corona are only visible during solar eclipses. The photosphere is the actual part that you see. The photosphere is also the apparent surface of the sun, which gives us the temperature of the sun. And then underneath the photosphere, you have the solar interior. If you notice, the temperature increases as you see how it looks like here. The temperature is increasing as it goes down. Okay, so as you get closer to the center of the sun, it's going to be hotter and hotter and hotter. Well, here at the photosphere, it's roughly at about 5,800 kilometers. That was not 5,800 Kelvin. And then it's going to increase in temperature as you get further and further from the photosphere. Okay, heat flow goes from the inside to the out. All right, so the photosphere, what is it? Well, the photosphere is the surface layer of the sun. It's the part that you quote-unquote see. Right? It's a gaseous surface that's less than 500 kilometers deep, not very deep. It has a temperature of about 5,800 Kelvin, and it's a thin layer of gas, which is going to give off heat and light. It's the part that absorbs and re-emits radiation produced inside the solar interior. So when the hydrogens are fusing to make helium, which is where all the energy comes from, it gives off gamma radiation, and that radiation is absorbed and re-emitted in lower energy radiation so it doesn't kill us. And we'll talk about that in class. All right, below the photosphere, the gas is denser and hotter, but it can't escape because the gas is above it from the photosphere and the chromosphere. Let's see. In good photos, you'll see the photosphere appears to be molten with dark edged regions. We'll see that in just a second. Here, okay, so if we were to look at the photosphere is the part that you see, the chromosphere is above it in those nice pink, orange peaks, and then the corona would be this blue part here, which is what you see in this total solar eclipse. All right, so in the photosphere, energy is made in the center of the sun and it goes outward. The energy goes outward through a little process we call convection. All right, we all know convection. Convection is, well, we don't want to see that. That's not good. All right, convection is when in a fluid heat rises and then the cool stuff sinks. So hot stuff rises, the cool stuff sinks. Right? Pretty easy. Okay, bubbles of hot gas rise up, the cool gas sinks down to the bottom, and yeah, it doesn't matter. Okay, so these bubbles that we see are called granules, and they last for about 10 to 20 minutes. They're roughly about the size of Texas, and they're constantly being replaced by convection. Okay? All right, so granulation is the process of these granules, right? It's these granules that occur, and this is what it would look like if we were to look at a good, and this isn't a good photo, but it's good enough, a good photo of the sun, and it appears molten, because if you look, it kind of looks like it's molten, and all of these are granules. All right, so the chromosphere is right above the photosphere. It's where visible UV and X-ray lines come from highly ionized gases. It's a lot fainter than the photosphere. You see it in a total solar eclipse as a line of pink just above the photosphere. All right. It's a low density excited gas, and it's roughly about 4,500 Kelvin right above the photosphere. But as you go from the photosphere, see how the temperature stays kind of about the same. Once you get up to this area, the transition period, it goes from 4,500 Kelvin to about 10,000 Kelvin, so about right here, and goes through the transition period, and it jumps up to close to about 1,000,000 Kelvin, and then you're in the corona. Okay. This spot here, like I just said, is the transition region where it goes from 10,000 to 1,000,000. In this chromosphere, you'll see these things, actually this is in the photosphere, you have these things called filaments, and these filaments are these dark regions here. It looks like streaks across the sun. They're really not that dark, but they look dark because everything else is brighter. In the chromosphere, you also have these spicules, which are filaments of cooler gas. Those filaments I just showed you. Let's go back. Okay, filaments here, these cooler gas regions, right? Okay, so spicules are filaments of cooler gas from the photosphere that rise up into the chromosphere. Okay. Each one lasts about 5 to 15 minutes. All right, so the layers of the solar atmosphere, we have, if we were to look at these, in visible light, we would see, this is what the sun would look like, and these nice little spots right here are called sunspots. If we were to look at it through ultraviolet, it doesn't look as calm anymore. It looks kind of crazy. And again, here are your sunspots. We're going to talk about those in just a moment. More sunspots. All right, sunspots, sunspots, sunspots. All right, so coronal activity here. So if we were to look at about, just kind of taking pictures of the different layers of the sun's atmosphere, this would be a picture of the photosphere. This would be a picture of the chromosphere, and this would be a picture of the corona. Okay. We didn't talk too much about the corona. Let me talk about that. It's the outermost part of the atmosphere. It's so dim you don't see it from the Earth's atmosphere. It's visible only during total solar eclipses, and the temperature of the corona rises with altitude. Let's see. I think that's about it. All right, moving on. Solar wind. So solar wind. What is solar wind? It's the wind of the sun, right? Okay, so it's a constant flow of particles that come off of the sun. The velocity of these particles is roughly anywhere between 300 and 800 kilometers per second, which is pretty fast. If you don't think I'm telling the truth, do the work. It's pretty fast. And because these solar winds are leaving the sun, and we'll talk about why they happen soon, the solar winds lose a mass from the sun of about 10 to the 7th tons per year. Okay, now it sounds like a lot because you're like, oh my gosh, 10 to the 7th tons, that's a lot. Oh my gosh. Well, it's constantly regenerating a lot of the gases, so that's not a bad thing. So it's really only losing 10 to the negative 14th of its mass per year. So if you really wanted to think about that, you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1. It only loses that much mass per year. It's really not that much. Okay, we're gonna be safe. All right, energy production in the sun. So in the sun, all of the energy is generated in the sun, and this is how all the other stars happen as well, in the core by nuclear fusion. So what is nuclear fusion? Well, it's where you take two or more light nuclei and you push them together and you shove them together and you bombard them together so that they make these heavier elements or these heavier nuclei. Okay, so you can take hydrogen and fuse it to make helium, lithium, boron, we keep going until we get to nitrogen. Right? Essentially, you can fuse every single element until you get to iron. I said nitrogen. I meant iron. All the way up to iron. But anything heavier than iron is made by breaking down of nuclei from uranium. So you take the uranium nuclei and you break it down, and that's called fission to make anything that's greater than iron. Okay? So how do we fuse these two? Well, you take two hydrogen ions, you shove them together, you lose a positron, you get a hydrogen 2, which is a deuterium isotope of hydrogen. In that process, you're also going to have a neutrino come off, right? Yay, neutrinos are great. Okay, and then you're going to bombard that with another hydrogen ion or another hydrogen atom. Where did my little... There it is. All right, so we bombard it with another hydrogen atom, and you're going to end up with helium-3, which is helium with a mass of 3. That's not good. We don't want helium-3. We want helium-4. Helium-4 is the stable one. So what do we need to do? Well, we need to take a helium-3 and a helium-3 and shove them together. Okay, so then you're going to lose a hydrogen and a hydrogen, but you have helium-4, which is the one you want. In that process, you're losing these neutrinos. You're also losing gamma radiation, which is not very good for you, just in case you didn't know. All right, there's just a bunch of stuff here, yada, yada, yada. We don't really care. Okay, the solar neutrino problem. So let's talk about these neutrinos. All right, these neutrinos are... where did I have it? I've got it written down in here somewhere. Here they are. They're produced in the core of the sun. They're like photons, but they don't interact with other particles. Okay, and these average neutrinos can pass through a lead wall that's as thick as a light year with no problems. Yeah, just right through, right? Yeah, that's some pretty powerful stuff. You can't detect them, and they don't interact with anything, so you don't ever feel them. But guess what? You have 10 to the 12th solar neutrinos going through your body every second. What? Yeah, that's a lot. Okay. All right, moving on. So, sunspots. What are sunspots? Well, in sunspots, they are linked to the sun's magnetic field, okay, because they come from the sun's magnetic field. They're cooler than the photosphere, so they're roughly about 4240 Kelvin, whereas the photosphere was about 5800 Kelvin. They look dark, but they give off a lot of radiation in those spots. All right, so here is a sunspot. Here is a sunspot. If this is the size of the Earth, this would be about the size of the Earth. This one would probably be about twice the size of the Earth. All right, they look dark, but if you think about it, they're actually pretty bright. They're giving off radiation still, and they're giving off a lot of radiation. They're still brighter than the full moon if they're placed in the sky, but they look dark because they're up against all that other stuff that's coming off of the sun. They are typically 2 times the size of Earth. They can last a few weeks to about 2 months, and then they'll shrink away. And they usually occur in pairs or in complex groups. And there was a time called the Little Ice Age between 1500 and 1850 when there were very few sunspots. Maybe there's a correlation there. All right, so sunspots. Here, let's talk about them some more. Here's some visible sunspots or visible radiation sunspots. These are from UV sunspots. Okay, so this is just visible photograph and a UV photograph. So it's taking pictures of different types of radiation. The active regions would be those, either the dark and the visible or the bright and the UV. Okay? And the active sun is, if we were to take a picture of the sun with an X-ray, this is what it would look like. Okay, so it's showing now the X-rays that are being given off. Okay? Pretty cool, huh? All right, so the solar cycle is an 11-year cycle of sunspots that are caused by changes to the sun's magnetic field. Okay, so it happens every 11 years. During that time, the sun is made of gas, so some parts of it rotate faster than others. And the equatorial regions, or the regions of the equator, the photosphere rotate faster than the higher altitudes. And this is called differential rotation. It's linked to the magnetic cycle. So what happens if you'll notice here and here, there's been a reversal of magnetic polarity in the sun because the field becomes tangled. And the nearby regions will change to compensate with that tangling. So it actually reverses the magnetic field of the sun. It's pretty cool. All right, so this causes an 11-year cycle of sunspots. And there we go, after 11 years. Okay, so I'm getting ready to run out of time. This is the end of part 1. We'll do part 2 in just a minute.